In special relativity, the concept of a four-vector is very important. It is a way to understand how space and time are connected. Traditionally, we think of space as having three dimensions: length, width, and height. However, when we think of time as a fourth dimension, we need a new way to describe the physical events that occur in this four-dimensional space-time. Imagine that you are navigating through space, moving along three familiar dimensions. But according to relativity, time is not a separate entity. It is interwoven with space, creating a unified fabric called space-time. When you move, not only does your position in space change, but your position in time also changes. This idea is captured by the concept of a four-vector. A four-vector has four components: three spatial components and one temporal component. You can think of it as a vector pointing through a four-dimensional space-time in which the three spatial directions and the temporal direction are treated equally. This approach elegantly captures the symmetry of space-time that Einstein proposed. In classical mechanics, when you rotate a vector, its length remains the same even though its direction changes. Similarly, in relativity, when you transform a quadruple vector by changing your frame of reference, using a Lorentz transformation, its length in space-time remains the same. This invariance is a fundamental principle of relativity. For a practical example, let's consider momentum and energy. In classical physics, momentum is a three-dimensional vector that describes the motion of an object in space. Energy is a separate quantity, but in relativity, we combine them into a single quadruple vector. The three spatial components of this quadruple vector represent momentum, while the fourth component represents energy divided by the speed of light. This unified explanation helps us understand how energy and momentum are related in a relativistic context. When we define momentum and energy together in this four-dimensional framework, we see that their relationship remains consistent across all frames of reference. This means that the fundamental relationship between an object's energy, momentum, and mass remains the same, regardless of how we are moving or how fast we are going. This connection shows us that time and space are not separate entities, but are fundamentally interconnected. It affects how we perceive events, distances, and durations, and reveals the true structure of the universe as a dynamic fabric of space-time. Quadruple vectors also play an important role in various areas of physics, such as electromagnetism and quantum field theory. For example, the quadruple potential in electromagnetism facilitates the covariant formulation of Maxwell's equations by combining the scalar potential and the vector potential into a single quadruple vector. By treating time on equal footing with space, the quadruple vector embodies the merging of space and time into a single entity, transforming our understanding of the universe from a static stage in which events unfold to a dynamic structure in which space and time are intertwined. It combines spatial and temporal components into unified entities that transform consistently under Lorentz transformations, preserving the fundamental invariance of physical laws in all inertial reference frames. In examining the structure of the laws of mechanics under the influence of Lorentz transformations, we are ready to consider a more comprehensive framework. We have previously examined how length and time transform under relativity, but we have not yet considered the role of mass. To understand Einstein's adjustments to Newtonian mechanics, we must begin with Newton's law, which states that force is the rate of change of momentum. Traditionally, momentum is defined as the product of mass and velocity. However, this definition needs to be refined when we include relativistic effects. In relativity, an object's momentum is adjusted to account for the effects of traveling at speeds close to the speed of light. Essentially, as an object moves faster, its effective mass increases, causing its momentum to increase more than it would in classical mechanics. Under this relativistic adjustment, the principle of action and reaction still holds. This means that forces still come in equal and opposite pairs, satisfying the conservation of momentum. However, the quantity that is conserved is not the classical product of mass and velocity, but rather the relativistically corrected momentum. To understand how momentum changes with speed, consider that in classical mechanics, momentum is directly proportional to speed. This relationship is approximately true in relativistic mechanics for speeds much lower than the speed of light. However, as an object's speed approaches the speed of light, the increase in its momentum due to its effective mass becomes much more pronounced. This leads to an important insight. If a constant force acts on an object for a long time, in classical mechanics, the object will continue to accelerate forever, potentially exceeding the speed of light. But relativity forbids this. Instead, as the object's speed approaches the speed of light, its momentum increases significantly, making further acceleration increasingly difficult. As a result, the object's speed approaches the speed of light but never reaches it. This infinite increase in momentum means that the object acquires significant inertia, resisting further acceleration. We can observe this effect in a simple system, such as a gas in a tank. When the gas is heated, the molecules increase in speed, which increases their effective mass. This makes the gas heavier. To quantify this, we can use a mathematical approximation to show that for small velocities, the increase in mass is proportional to the square of the velocity. As the temperature of the gas increases, the average speed of the molecules increases, causing the relative mass to increase. Thus, the mass of the gas increases in direct proportion to the increase in its kinetic energy divided by the square of the speed of light. The observation that energy and mass are equivalent led Einstein to come up with a groundbreaking idea. The total energy content of an object can be expressed as its mass multiplied by the speed of light squared. The equation provides a complete representation of the relationship between mass and energy and is consistent with relativity physics. Typically, energy changes correspond to extremely small changes in mass because converting significant amounts of energy from a material requires an enormous amount of energy. The equivalence of mass and energy has been rigorously tested and verified through both theoretical derivations and experimental verifications. The implications of this principle have profound implications spanning particle physics, cosmology, and energy production technologies. For a detailed analysis of this equation, the term on the left represents the total energy of an object. The last term is considered ordinary kinetic energy. Einstein interpreted the large constant term, the energy of mass at rest, as an intrinsic part of the total energy of an object, and this was called rest energy. When a force acts on an object with rest energy, it moves it and gives it kinetic energy. In classical mechanics, the rate of change of energy is equal to force times velocity. As an object's energy increases, its mass increases. This increase in mass is implicit in the original assumption. As long as the force continues to act, both energy and mass continue to increase. To solve for mass, we need to manipulate the equations that contain energy and force. By doubling and integrating both sides of the equation, we find a relationship that connects the square of the mass times the speed of light squared to the square of the mass times the speed squared plus a constant. We examine the special case where the speed is 0, defining the constant as the rest mass energy. Using this constant, we derive the famous relationship between relativistic mass and rest mass. This relationship shows that an object's mass increases significantly as its speed approaches the speed of light. This increase in mass is what prevents any object with mass from reaching the speed of light, as it would require infinite energy. For example, an atomic bomb with a blast energy of 20 kilotons shows that the remaining material after the explosion is about 1 gram lighter due to the energy released, obeying the relationship d/d, Mc2. This mass difference corresponds to the energy released, as defined by the relationship between energy and mass. One of the most convincing experimental confirmations of this theory involves the annihilation of an electron and a positron. When these two particles, each with a rest mass, collide and annihilate each other, they produce 2 gamma photons. The energy of these photons is equal to the energy of the combined rest mass of the electron and positron. This experiment directly demonstrates the conversion of mass into energy. Thanks for listening. Stay well.